between a fraction and a rational number. A rational number, look at the first 5 letters of the word rational, by the way, ratio, right? So it's a ratio, it's a quotient of 2 numbers, the second one not 0, but 2 whole numbers, 2 integers. So for example, every real number, which is what comes up next, I'll put it down, every real number can be expressed as itself over 1, but it doesn't make it a rational number. So let's take a look now at, again, this is meant to be a fancy R. Well, I really have to thank you with admiration for getting the idea of, maybe even though it was just working, it decided not to work and just plugging it in and it made it work. Now I still can't turn the camera around, but that I guess is somewhat minor. And it just seems strange that it worked before and then stopped working as soon as I tried to get it to work in public, so it didn't. So this is the set of real numbers which are all numbers that you can depict on the number line. Let me just write numbers expressible as, you can write them as decimals. And as you know, if you've taken mathematics 4010, there was a time when I was teaching either 4010 or 4100 or both every term, but I just really got tired of teaching 4010 with all the annoying arithmetic at the beginning when you're setting up Gauss-Jordan row reduction and inverting matrices. So prefer doing this. These are the numbers that you study in 4010 in advanced calculus. I still call it that. They renamed it. I wasn't in favor of the renaming. Fundamental analysis 1, I think. So the set of real numbers consists of the rational numbers together with all the numbers that are not rational, which of course are called irrational numbers. And as some of you may know, the rational numbers are distinguished from the irrational numbers, and you'd see a proof of this in 4010 or maybe elsewhere. Actually, I could do it, but it's not part of the course, and I'm not looking for digressions, interesting and informative though they may be. The rational numbers are precisely those real numbers that are expressible as repeating decimals. That is, they repeat in certain blocks. So for instance, the number 0.23232323, the 2 threes repeat as a block of 2. That would be a rational number. It's very easy to convert a repeating decimal to fractional form. If we had time, I would go into it. If anyone's interested, you can stay after class. I'll quickly show you 2 ways to do it. One is by looking at it as a convergent infinite geometric sequence, and the other just uses simple algebra, whereas non-repeating decimals are irrational, cannot be expressed in the form a over b, and perhaps later in the term we'll prove, for example, that a number like the square root of 2 is an irrational number because there's no way to express it in the form a over b as a rational number. So people will go around sometimes and glibly say, oh, anything's possible. Well, no, not anything's possible. For instance, the Greeks knew this. It's not possible to express a number that squares into 2, right? That's a definition of the square root of 2. It's a number such that it squared, it times itself, gives exactly 2. You can get close to 2. You can get arbitrarily close to 2 by taking more and more decimal places. Like if you take 1.414 and you square that, you'll get close to 2, but you will not get to 2. If you take more decimal places, you'll refine it. You'll get ever closer to 2, but you'll never get there in any finite number of digits. So numbers like the square root of 2, and I don't know if we have time, we may show that the square root of any non-perfect square is actually a non-perfect square is a number whose square root is not an integer. So for instance, 25 is a perfect square, 36 is a perfect square because it's the square of the integers 5 and 6 respectively. But other than that, if the square root of a number is not a actual whole number, then it's no rational number at all. It's not expressible as a quotient of two integers, the second one not zero. So maybe we'll look at that later in the term. Next term, we'll be able to generalize that very simply into a theorem that says the nth root of any non-perfect nth power is no rational number at all. So in fact, as those of you who've taken 4010 have seen, there are actually, oddly enough, more irrational numbers than rational numbers. Even though there's an infinite number of rational numbers, there are even more irrational numbers. So in fact, there's an entire hierarchy and a sequence of ever-increasing orders of infinity, which is totally extremely interesting, but I won't go into it now. We'll conclude this by taking a look at the set of complex numbers. I'm doing this just sort of for review and for completeness. We're not going to be dealing with these other sets. But as long as we're talking about these symbols, the set of complex numbers, and those are numbers, as you should know. Let's make this, erase the comma, and make it into a colon to conform to the rest. These are numbers of the form a plus bi, where a and b are real numbers. So remember how we're going to show a and b are real numbers? We're going to write a and b are elements of R, the set of real numbers, and I has a property that it squares into -1. So we will develop all those systems axiomatically in abstract algebra next term. Abstract algebra is also called modern algebra for reasons that I'll explain. But for now, let's take a look at, should I erase this, leave it, go to another board? I'll go to another board. Okay, so this will be board 2. So I can still go back to this board if you should need it. But let's work on this board. Okay, so we were saying that you don't have to know terms like ordered integral domain this term, but that's what it is. And as I said, on Tuesday, we'll deal with this in more detail in modern algebra or abstract algebra. But I might as well use the correct terminology. Forms, the set of integers forms an ordered, I hope you can read my writing. I sort of print or use italics so it's more legible, but with this slippery surface and this plastic pencil on it, forms an ordered integral. So the domain is a set with particular specified properties. Ordered means you have a relation, a binary relation of greater than or less than, and integral is an adjective for integer. So let me leave a little room on the left. You'll see why. Okay, so property 1, closure for addition. So we'll start by setting, so I don't have to keep repeating this, that A, B, and C be any integers. Okay, so if A and B are integers, then A plus B is an integer. A plus B is in the set of integers. So again, we were looking at it. We took a look at some examples and counterexamples of closure on Tuesday. For instance, we saw that the negative numbers, and I'll just say numbers now, it doesn't matter whether they're real numbers, rational numbers, integers, although we're thinking of integers, is not closed under multiplication, a set of negative numbers, because if you multiply two negative numbers, you jump outside the set and you go somewhere else. The set of integers is not closed under division because it's possible to take, notice it's possible. just because in some cases, namely whole numbers, you can do division by 1 and stay in the set, but not always. For instance, you can't divide 1 by 2 and stay in the set of integers. So that's not closed. Let's look at 2 important properties. What would you say, and we talked about this Tuesday, let's just repeat, what would you say about the set of positive integers under addition? Is that set closed under the operation of addition? It is, right? And how about multiplication? So the check is, if you multiply 2 positive integers, do you again get a positive integer? The answer is yes. So the set of integers, the set of positive integers is closed under addition and multiplication. We'll come back to that when we get back to order. But for now, let's take a look at associativity, or the associative property. Associativity for addition or the associative property. Some people say the associative law. So as we were saying Tuesday, if you have 3 numbers, as someone said encouragingly, either last Thursday, not Tuesday, that I might conceivably, it was last Thursday, actually get to like this. I can almost see that I might get to like it. It still doesn't duplicate seeing you, but so here we are adding 3 numbers, and again, addition being a binary operation, you can execute only one addition operation at a time, and so we can indicate that by, if we add the first 2 first, and then add the third one, but the other way to associate, put together, people you associate with, people you're together with. So this says, hold the A in abeyance and leave it there. So you have A plus, and now doing what's in parentheses first, you take B plus C, and then you go back and take A plus that result. And what the associative property, you can always associate them, I just did it. No, it's, I could record it, but the only thing you're going to see is me when I get back to, or maybe you if you haven't shut your video off, because I'm told that that the disadvantage, there's some advantages to whiteboard, but the disadvantage, the main disadvantage to whiteboard is it does not copy. As Professor Ronan said, it's either impossible or close to impossible. Whereas with OneNote, which I'll be up to speed with on Tuesday, that will be able to record. So please, for the moment, just as if this were a whiteboard in school and you were copying it, please just do that. Unless, I don't know, some of you may be able to take, do you call it a screenshot? I don't know how to take a screenshot myself, but maybe you can take a shot of this screen if you want. Otherwise, just take notes as if it were a whiteboard in school. So as I said, this simulates a whiteboard. So the essential thing about this is not the grouping. You can do the grouping. The essential thing is that they're equal. And again, as we were saying Tuesday, if everything were associative, you wouldn't have a separate name for it. So why don't you check for yourself and see whether subtraction is associative? So what would you look for? I'll write this, but then I'll erase it because I don't want to confuse you. So for subtraction, it would look like this if you're subtracting, if you're subtracting 3 numbers. So again, you could catch the first 2, or you could catch the second 2. And why don't you, at your leisure, if you ever have leisure, make up a numerical counterexample to show that in general, remember, if something isn't always true, then it's not true. I can't put an equal sign there. But as we said Tuesday, or maybe last Thursday, to disprove something, all you need to do is come up with a single counterexample. So why don't you do that and make sure you see that subtraction and division are not associated. So let me get rid of this. Now we have the existence, that means there is one, existence of an additive, because we're still talking about addition, identity because if you start with anything and additive, so add the identity 0, so let me put in what it is. So we'll call that 0, that's circle, and as I said, it's actually a little bit oblong vertically. It's called prolate. Oblate is extended in the horizontal direction. Prolate is extended in the vertical direction. So like if you have an ellipse anyway, I assume you can read my zeros and then I'll be able to read your zeros. So this has the property that when it's added to any integer 0, a, on either side, you get a. So a plus 0 equals a, and that also equals, what a mess that is. A plus 0 equals a equals 0 plus a. So far I've said an additive identity, but there's only one. We already mentioned that. So how would you prove that there's only one? How in general in mathematics do you go about establishing uniqueness, that there's only one? Anyone want to unmute themselves and say, anyone who knows? How would you prove that this isn't really part of it? Maybe I shouldn't interrupt here. I'll put it into parentheses.
Suppose they're 2 and then show they're equal.
Yeah, there you go. Very good.
Can you repeat that? How do you...
Yeah.
Suppose they're 2 and then show that they're equal.
I wish I could see who's saying that.
Duncan.
Duncan. Oh, all right. Duncan Panoff. Very good. Okay. At least you don't have to worry about commuting into Manhattan now. You can be here anyway. Yeah, I keep track of my students. Let me repeat for those who weren't here before, and I'll email it to you. You don't have to show yourself, but you do have to use your real name, because that's all I have a list of. I mean, unless you want to, I don't know, email me with some sort of other name, but that might be difficult. But as it is, the class list shows your legal official school name, whether or not you use it. So if you want your attendance recorded, and I will be looking at the attendance, you just have to use your school name. That was a little traumatic for me, having two names. In the first grade, I never went to kindergarten. It wasn't mandatory, and I didn't go to kindergarten. And I guess they had pre-K then. But anyway, so I started the first grade. And the first day of the first grade, the teacher went around and asked our names. And she said, well, it's easy for you. You have just one name to know, my name, the teacher's name. And she had to learn, 30 of us or whatever it was. And I thought even then, no, that's not true. We have to know each other's names too. But anyway, so she asked our names, and I was, my name being Alfred, some people called me Alfred, some people called me Alan, some people called me Fred. So I suspected I should say Alfred, but I wasn't quite sure. So I didn't say anything. And, my teacher must have thought, oh no, here, I have a 5-year-old who doesn't know his own name. A dog knows its own name. I have my work cut out for me. But anyway, we kind of got over that. So the additive identity is unique. And as Duncan said, yes, that's precisely how to do it. Assume or another way to say that is assume not. Assume or suppose, say 0 and say 0 prime. 0 prime, you know that, right? Are both additive identities. Let's compute 0 plus 0 prime in two ways. So I've left some room, you notice. So 0 plus 0 prime, since 0 prime is an identity. So since 0 prime is an identity, look at what an identity does here on step 3. It adds on either side to whatever it's adding to and leaves that same thing. So look, we're starting with 0, and now we're adding the additive identity 0 prime. And when you add an additive identity to any number such as 0, you get that same number, which is 0. On the other hand, looking at it this way, here, since 0 is an additive identity, so the additive identity adds on either side and leaves the other number the same. So if you take the additive identity 0 and add it to this other number 0 prime, well, when you add an additive identity 0 to 0 prime, you're left with 0 prime. And so we see by what's called the transitive property of equality. The transitive property means you can so this says A is equal to B, but if B is equal to C, then we can make, you know, what transit means? You can make the transit and jump straight over and say A is equal to C. Another example of a relation that is transitive is greater than. If A is older than B, and B is older than C, you'll certainly agree that A must definitely be older, maybe much older than C. So again, so the transitive property or transitivity, and we will come back to this later, this term, transitive, is that right? Transitivity, yeah. So you know the symbol for it implies, it means it leads to, or that would be a conclusion. So look, if A is bigger than B, and then B, it's greater than, in turn is greater than C, then we can jump across and say A is greater than C. So that's called the transitive property. And as I say, when we take a look at equivalence relations and congruence modulo n later in the term, we'll see some more of that. So let's continue with property 4. So I'm going to go to a new board. Oh, okay. So this will be board 3. So up to property 4, existence of additive, because we're still talking about addition, inverses. There is, or there exists, and the symbol for that, as many of you know, is a backwards capital E. Yeah, like, whoops. So backwards capital E means there exists or there is, or for some number, there exists some number. There exists, put an S on there. There is or there exists a number an integer. And again, saying that, and I'm not going to write this, you can write it yourself, but you've known it for a long time. That's read negative A. And as I said Tuesday, please not minus A. Negative A is an element of Z. That means negative A is an integer. And then the colon means such that, or with this property, A plus this number negative A, and it has to work on both sides, negative A. By the way, we don't use two of these symbols together. We don't write. You can't write that. Don't write that. Use parentheses the way I just did. A plus negative B. Look at that, I'm getting adept at this. I can write, I can erase. I can't get into it in the beginning because I didn't realize that. Okay, plus A. So the negative of A, whose role or function is the additive inverse of A, gives you the additive identity. So a number plus its additive inverse. So the inverse undoes it, does the opposite. A number plus its additive inverse gives the additive identity. It's not hard to remember which is which. Identity means it leaves it identical. Inverse is the opposite. Okay, I said I was leaving room on the left because I wanted to write something, but since we're on different boards, instead of, I was just going to put like a brace around it and say those four properties. Again, this algebraic terminology isn't required for this class, but I'll just mention that any set, and by the way, I'm talking in terms of integers here, but everything I'm saying, all these properties hold for any set that has addition on it. Well, I mean, any set that that has those properties. In other words, A doesn't have to be a number, it can be something else, but its additive inverse, if there is one, would have the property that gives the additive identity. So any set with let me for emphasis, I was going to write an operation. Let me say a binary operation because it deals with two at a time. Again, you know, we speak of a binary operation. If there were only binary operations, we wouldn't have a special name for it. But for instance, the squaring operation is a unary operation. You need just one number to square. So, you know, 10, when you perform that one operation of squaring, is 100. There are ternary operations. You can go back to mathematics 30, 20, 30, 30, or 30, 50 now they have, I guess. let's take, for example, the norm of a three-dimensional vector. So you're doing something to the components of the vector, and you're getting a non-negative real number, right? The norm, the square root of the sum of the squares. So here we have a binary operation. That has properties 1 to 4 is called a group. And then, of course, we talked about this commutativity. Again, you can always commute or change the order of two numbers. The question is, are the results the same? And the commutative property says, yes, they are. And of course, we know that subtraction, for instance, is not commutative. A minus B is not the same as B minus A. What's the relationship between A minus B and B minus A? What is the fraction A minus B over B minus A equal?
-1.
Yeah, it's -1. That's right. Whatever numbers I used on Tuesday, 10 minus 7 is 3, 3 minus 10 is -3. So they're the same except for the sign. So when you divide them, you get -1. And of course, obviously, division is not commutative. Certainly 2 divided by 3 is not the same as 3 divided by 2. Or 2 divided by 1 is not the same as 1 divided by 2. So a group has just one binary operation, whatever you want to call it. You can call it addition, multiplication, or something else. But so with property 5, it's called a commutative group for obvious reasons. As I mentioned on Tuesday, Abel was, along with Galois, one of the founders of abstract algebra. Both of them died. Galois Evariste. Whoops, I left out an S. Galois died when he was either in his late teens or maybe his 20. Don't think he was 21. He got sort of obliged to engage in a duel, and he knew he would get killed. It was a political setup, and somehow the night before, he knew basically he was about to die. He sat down and wrote a treatise that was so recondite, so difficult to understand, that it took mathematicians several decades, and people just gave up on it. It looked so crazy. And it was, where does genius come from? He established, field theory. One of you asked about fields on Tuesday, and Galois theory. I won't go into what that's good for, but it's good for a lot. Abel also, I think he died of tuberculosis. He was only 28 or 29. So, you have to wonder what these people might have, given a normal life, been able to contribute. Okay, so then property 6, closure under using the dot for multiplication. So it says that if you multiply, as we said on Tuesday, you can write this as AB. So you can write this as AB. You can write this as a parentheses around the B. You can have the parentheses around the A and just the B. You can have parentheses around both. This really works nicely when it works. Just tap eraser and it erases nicely. So when you multiply two integers, you stay in a set of integers. That's called closure. And we also have associativity for multiplication. And that, as you know, says AB times, see, I'm leaving out the dot. I'm just using juxtaposition, putting them next to each other, equals A times BC. And you know what you should do in any of these things? I mean, it's fairly trivial. It's just little definitions. But in anything you do, including some of the homework that I'd like to give you, and it's 5 after 7, maybe 6 after 7, but I want to go on a little longer. Make up some examples. Sometimes looking at an example, if you can, first of all, fortifies your conviction that it's true in the first place, and secondly, you might gain some insight into how to go about actually proving it. That would be particularly useful when we do mathematical induction. But even with greater than, less than, I'll put down some things for you to do. And property 8. Is the distributive property, or some people say law. What is number 7? Associativity for multiplication, or the associative law for multiplication, dot meaning multiplication. Okay. Distributive property of multiplication over addition. So it says if you have multiplication and addition in parentheses, so this is the one that unites the addition operation and the multiplication operation. Yes, yeah, that's exactly, that's what 7 says. You can all see it when someone posts one of those quick things that's only fleeting. I guess you can. If I can see it, you can.
Yes.
So this says, yes, okay, all right. Use that to say, yes, that's visible. Okay. So as I was saying on Tuesday, the number outside distributes itself, gives it over to each number inside. And again, I'll repeat, but not right. The order of operations says that in the absence of parentheses, like in the last thing I wrote, AB plus AC, in the absence of parentheses, you prefer multiplication and division first. That takes priority, and then you do the addition. So that spares you from having an excessive number of parentheses. And because it may not be commutative, we actually have to say that if you have B plus C first times A, then it's B times A plus B times C. So you have to keep the order the same because not all systems are commutative. This set of integers is commutative, but for completeness, I'm putting that down. And I think we mentioned, some of you know, a very prominent, important system in which multiplication is not commutative, namely what? Matrices, right? In general, matrix A times matrix B is not equal to matrix B times matrix A. In fact, if the dimensions aren't right, I mean, an M by N matrix only multiplies an n by p matrix and gives you an m by p result. But if you switch that around, you can't even do the multiplication. So let's go on to another board. And I guess we're up to, wait, what are we up to? 4, okay. Okay, these 8 properties say Z forms what's called in algebra a ring. Now we have some optional properties of a ring. In other words, you may or may not have them. For property 9, well, here's no particular order. Commutativity for multiplication, again, it's multiplication. And of course, that says A times B equals B times A. And as we were just saying, the matrices, 2 by 2 matrices, let's say, form a ring, but it's not a commutative ring. And also, so that corresponds to the 5th property, namely commutativity for addition. And we have something that corresponds to the 3rd property. So every ring has an additive identity. In the numbers, it's called 0. But not every ring has a multiplicative identity, but the integers do. So, but not all rings do. Existence of a multiplicative, that just means under multiplication, a multiplicative identity. And as we discussed Tuesday, and as you've known since elementary school, the multiplicative identity is 1. So 1 times A equals A times 1 equals A itself. So again, identity, it leaves it identical. You start with A and you multiply it on either side by the identity, and you're still left with A. And we won't go further building up the last major system of abstract algebra here, except to mention that property 11 would be existence of multiplicative inverses for non-zero numbers. So the integers don't form a field because, for instance, well, as a matter of fact, there are only 2 integers that have multiplicative inverses. So the multiplicative inverse has to multiply to give the multiplicative identity 1. Well, the only 2 integers that have multiplicative multiplicative inverses are positive 1, because its inverse is 1, because 1 times 1 is the multiplicative identity, 1, and negative 1, because negative 1, that has a multiplicative inverse. It's negative 1 itself, because negative 1 times negative 1 gives the multiplicative identity 1. But for instance, 2 does not have a multiplicative inverse. It would be 1/2, but that's not in the set of integers. So now let's, so far we have if you have all this, you have a commutative ring with unity. Unity being the multiplicative identity. So again, all these things in algebra, and when you say algebra in college, you don't mean, high school algebra is just things you can do with numbers. Algebra means abstract algebra. So all these things will build up from
Dr.
scratch.
Freeland?
Yeah.
Just to reiterate something. So on number 10, we have a commutative ring with unity and multiplicative identity.
No. The multiplicative inverse is called unity. It's the same thing. It's not two separate things.
Okay.
We often just say with unity rather than with multiplicative identity. So order. So let's go back to recall what we said earlier. So that's where Z plus, I won't write what it is, but you can write it if you don't know what it is or can't figure it out. It's a set of what? Positive integers, right? The set of positive integers is closed under addition, the common means end, multiplication. And this is called the Trichotomy Law, which right now we won't have that much use for, but I'll mention it. So I think I said something about trichotomy on Tuesday. Tri means three, so it's broken up into three parts. Namely, every integer is either
And is this property part of number 10, or is this a new property?
We're done with that. That's now we're talking about order. So we're going to get an ordered integral domain. So every integer is either positive, so say a is greater than 0, and next term I'll talk about why being positive is the same as saying a is greater than 0. But again, this term we're concentrating on properties of the integers, so things that you already, quote, know. I'll explain them further so you'll really know them next term. But you're used to saying a is positive and a is greater than 0 interchangeably, because the positive numbers are the numbers that are greater than 0. I won't go into it further now. Or a is equal to 0, or negative a is positive. I'll just say or. So every integer, I'll call it a. Every integer a is either positive, a is greater than 0, or a equals 0, or a is negative. And the negative numbers are the numbers that are less than 0. So each number a is in exactly one of those categories. Either it's bigger than 0, or it's less than 0, or it's 0 itself. The reason I make that point is ordinarily, you should notice, ordinarily in mathematics, when we use the word or, we use it in the inclusive sense. So if I say a is either a positive number or a prime number. Well, if a is 7, it's both. It's a positive number and it's a prime number. But you can't say, oh, you said or, so it can't be both. No, unless otherwise specified by saying not both or in exactly one, or is used in the inclusive sense, not the exclusive sense. So again, if I say, the number a is either positive or prime, well, if it's both, then, that's okay. And so what I'm going to, I think, leave you with is some, let's repeat the definition of greater than, and then let me leave you, it's almost 20 after 7, with some things to work on over the extended weekend. So by definition, and again, I'm not going to write it, but you can write it if you want, but I think you know it. A is greater than, bigger than larger than whatever you want to say, A is greater than B. And again, as I mentioned on Tuesday, if you have 4 is more than 3, the smaller part is adjacent to the smaller number, the wider part to the bigger number. And if you turn it around and write that 3 is less than 4, again, the bigger part is adjacent to the bigger number, the smaller part is adjacent to the smaller number. So, these are equivalent statements. A is bigger than B and B is less than A means that A minus B is in that category of being positive. And again, in any of these things, check it. 10 is bigger than 7. Well, let's check it. How do you check it? You see whether 10 over here, 10 minus 7 is positive, and it is. So 10 is, by definition, bigger than 7. So, okay, homework. Let's start a new sheet. Uh-oh, why is this not opening a new sheet? Oh, again, okay. So that was 4. Okay, so this will be 5. So prove each of these where A, B, and C are integers. If A is bigger than B, show that A plus C and A minus C is bigger than B plus C and minus C. So you do those separately. And show that why don't we do this? Let's do the transitive property first. If A is bigger than B and B is bigger than C, then prove that implies that
Professor, that's 2. The first
yeah,
the first thing
2.
in the okay, thank you.
As I say, it's kind of slippery to write with this. 3. If C is positive, then AC is bigger than BC, but if C is negative, then you reverse the inequality sign, you get AC is less than BC. So in property 3, we say that multiplication by a positive number preserves the inequality, preserves. If you preserve something, you keep it. And in property 4, if C is negative, we say that it reverses the inequality. It changes from this to this. So this reverses the inequality. I'll use that symbol for inequality. And this preserves, if it goes in the same direction, preserves the inequality. Let's show that if no, you don't have to send the homework to me. Do the homework. I want you to do the homework, and then as necessary, we'll go over it. But you have to be able to do it yourself. So actually do it. If A is bigger than B, and I'll put it underneath like that, then, okay, AC is bigger than BD. See, I made a list of things to okay, so for this one, we're going to require that A, B, and C, D are positive. For this one, if A is bigger than B and C is bigger than D, then A plus C is bigger than B plus D. So again, first you want to think about these. I made a list of things to prove that. Okay, I guess that's it. So, you know, first convince yourself. I mean, these are very simple and very trivial. Convince yourself that they're true. I mean, obviously, if A, in number 5, if A is bigger than B and C is bigger than D, and they're all positive, you can see what happens if they're not. You need positivity there. Then basically, what does 5 say? It says if you multiply two bigger positive numbers, then the result will be bigger than if you multiply two smaller positive numbers, right? A and C are the bigger ones. If you multiply the two bigger ones, and then B and D are the smaller ones, well, if you multiply the two bigger ones and multiply the two smaller ones, then the product of the two bigger ones will be bigger than the product of the two smaller ones. And this, similarly with number 6, if A and C are bigger than B and D, well, then if you add the two bigger numbers, the A and C, you'll certainly get a number that's bigger than the sum of the two smaller numbers. So anyway, on the basis of that, on the basis of the definition of greater than, why don't you carefully prove all those? Again, they're very simple. And
for number 6, we're also assuming that A, B, C, and D are positive, right?
No, they don't have to be positive. That'll be true. That'll be true in any case. If you add two bigger numbers and you add two smaller numbers. Let me leave you with this. I want to, on Tuesday, talk about divisibility and the division algorithm. But okay, you know what? I left out one thing for an integral domain. So let me put in that one additional thing. So, okay, 6. You might want to put this where it belongs, which is before, well, no, actually, okay, it belongs here too. What makes it an integral domain there are no, and we'll talk about divisibility and evenness and oddness on Tuesday. In an integral domain, there are no proper, I'll say what that means, divisors. So we'll talk about divisibility, but now I'm defining divisors of 0. So a divisor.
Professor, I don't mean to sound rude, but being the 7:30, I do have to go to another class.
Oh, well, yeah, some of you do. A divisor of 0 is a number A such that AB equals 0. So what do you know in the integers? If I tell you I'm thinking of two numbers and their product is 0, what can you tell me for sure? Yep. So, yeah, that's right. So a divisor of 0, and then we'll conclude this. That is, if AB equals 0, A equals 0, or B equals 0. So that's what an integral domain is. You have no proper divisors of 0. And later in the term, we'll see situations in which you do have proper divisors of 0. And I'll give you an example, but I won't take the time now. I made up two matrices. You can try it yourself if you want, but otherwise I'll give it to you on Tuesday, whose product is 0, and yet neither one is a 0 matrix. So anyway, with that, we will close, and hopefully on Tuesday, things will go more smoothly. But again, thank you for your indulgence and patience and help. You know, told me what to do. So, all right, everyone. I'll see you Tuesday. I mean, I'll stay here if anyone wants to, doesn't have class, wants to stay and talk a little bit. And eventually, as I said, I'll get the waiting room so I can talk to you individually if you want. But so here we go. I will.
Thank you, Professor. Appreciate it.
Okay. Have a good weekend. Good, holiday weekend, and see you on Tuesday.
Thank you, Professor. Good night.
Good night.
Good weekend, Professor.
Thanks.